Okay, we're back now to talk about reduction reactions. So we already talked about how to identify the difference between an oxidation and reduction reaction. And now we're going to look more specifically at the reagents you would use for those types of reactions. So let's start with reduction, because there are less reagents, so it's a little easier and the mechanism is easier. Reduction reactions. There are two main reagents that we use in organic chemistry to reduce carbonyl compounds down to alcohols, and it depends on what the carbonyl is as to which reagent you would choose. So I'm going to draw kind of a large looking molecule here, and you'll see why when we start talking about this. I want a molecule that has a lot of different functional groups on it. So I'm going to draw something like this. It has an alkene, a ketone, an ester, a carboxylic acid, and an aldehyde. Okay, so rather large molecule, but these reactions would work on smaller molecules as well. So depending on what kind of reduction you want to do, you could use a reagent known as sodium borohydride, NaBH4, or you could use a reagent known as lithium aluminumhydride. Lithium, aluminum, Al for aluminum, and then hydride, H4. If you use sodium borohydride, then at the end of the reaction, you usually need a proton source to protonate your alcohol. So methanol is usually used for that, CH3OH. If you're using lithium aluminum hydride, this is a much more reactive source of a hydride ion. So you have to do this in two separate steps. You add your lithium aluminum hydride, and then in a separate step, when everything is done, you add some water to protonate your alcohols that you made. So I would describe the difference in these as the sodium borohydride being a mild source. Of a hydride ion, H minus. And then lithium aluminum hydride is the strong source. Of a hydride ion, H minus. Notice it's a hydride ion, not a proton. We're not writing H plus. This is a really strong nucleophile, which makes it a great reducing agent because it will attack these carbonyl carbons that all have partial plus charges. So what ends up happening when you use sodium borohydride, since it's not as reactive as lithium aluminum hydride, it's going to basically reduce the most reactive of the carbonyl compounds. And you won't learn this until the spring semester, but you will talk more about it then. It turns out that ketones and aldehydes are the most reactive of the carbonyl compounds. So they're the easiest ones to reduce. So when you add sodium borohydride, only those carbonyl compounds will be reduced down to alcohols. So the product here, I'm going to redraw it. Nothing happens to the ester. Nothing happens to the alkene. That's not a carbonyl compound. Nothing happens to the carboxylic acid. But the ketone will get reduced down to an alcohol. And the aldehyde also will get reduced to an alcohol. So these carbons here and here have gone from a carbon with 2 bonds to oxygen, same thing here, down to a carbon. Each of those has only 1 bond to oxygen now. If you instead use lithium aluminum hydride, this is a much stronger source of the hydride ion, and it will end up reducing all 4 carbonyl compounds that I drew here. The only thing it won't react with is the alkene because this doesn't have a partial plus charge on any of these carbons. So there's nothing for that really strong nucleophile to attack. So the result here, we've got our 2 rings. The ketone is an alcohol. The ester gets reduced to an alcohol. Nothing happens to the alkene. The carboxylic acid gets reduced to an alcohol. And the aldehyde gets reduced to an alcohol. Okay, so that's the main difference to remember between these 2 reducing agents. is if you only want to reduce an aldehyde or ketone, then it makes sense to use the milder source of a hydride ion, sodium borohydride. If you want to reduce an ester or a carboxylic acid, or maybe even an acid chloride, then you can use the much stronger lithium aluminum hydride. But you don't want to use this if you don't have to, because it's more dangerous to work with in the lab. Okay, so next we're going to look at the mechanism for reducing aldehydes and ketones versus the mechanism for reducing esters. Carboxylic acids are a little more complicated because of that acidic proton, so you'll get into that mechanism next semester. But let's first start with the mechanism of sodium borohydride. Let's clear up our screen here. Let me try a different pen. This one's starting to wear out. Mechanism for sodium borohydride. So this is when we're reducing aldehydes and ketones. And if you happen to use lithium aluminum hydride just to reduce an aldehyde or ketone for some reason, it would follow the same mechanism. So let's take a simple ketone. Let's just do acetone. Sodium borohydride is a source of a hydride ion. So if you'd like to in the mechanism to keep it simple, you can just write out the hydride ion. In your book, they actually draw the whole molecule and show the hydride ion coming from that. Either way is fine with me. So this is a nucleophile, and if we look at our carbonyl compound, this actually is the same mechanism you saw for Grignard reagents. So it's not a new mechanism to learn. Just think about it the same way. You have an electronegative oxygen, so this carbon has a partial plus charge on it. And nucleophiles, things with minus charges, are attracted to electrophiles, things with plus charges, or partial plus charges. So that nucleophile is going to attack this partial plus carbon and kick electrons up to the oxygen. And that becomes a dot dot minus on the oxygen. And we've now added a hydrogen atom here. That's the beginning of my reduction. And at this point, there's nothing else to kick off the molecule, so the only thing that can happen is that oxygen gets protonate. And so that's what our solvent is doing in the mixture. It could be methanol, it could be ethanol, any source of a proton to protonate our alcohol. And there we go, there's our alcohol. When we did this reaction with Grignard reagents, it was exactly the same arrow pushing. The difference here was that I had an R, some sort of nucleophilic carbon group. But the rest of the mechanism was exactly the same. Okay, so that was aldehydes and ketones. Now, if you use lithium aluminum hydride and you want to reduce an ester, then we have an extra 2 steps in the middle. So I'm going to erase this and now draw on the mechanism for lithium aluminum hydride. Oops, let me try to get a pen. So this is going to reduce esters. Carboxylic acids, the mechanism is a little more complicated, so we'll leave that for next semester. So if I'm reducing an ester, let's draw an ester out here. CH3. The difference with esters, as opposed to aldehydes and ketones, is that they have this good leaving group attached to them. So we saw the same mechanism with Grignard reagents. The only difference here is that lithium aluminum hydride is a source of a different type of nucleophile, a hydride ion. So just like with sodium borohydride, it's going to attack this partial plus carbon. Nucleophile attacks electrophile. Initially, that kicks electrons up to the oxygen. Dot dot minus. I've added a hydrogen, and I still have on this OCH3. But now the difference here is that this is a good leaving group. We've got a great leaving group on there. And so the carbonyl compound says, oh, I can reform into a stable double bond to a carbon if I just kick out that leaving group. And so initially, in the middle of this mechanism, we reform our carbonyl, and our leaving group has left. And now we're at the stage where we have an aldehyde. But it's not going to stop there, because aldehydes are more reactive than esters. And so this lithium aluminum hydride, generally we use an excess of it in these reactions, or at least 2 equivalents, so that there will be more hydride ion available. And now we repeat the same mechanism that we saw for sodium borohydride. This nucleophile is going to attack that electrophilic carbon. It's going to kick electrons up. We have dot dot minus. Now we've added a total of 2 hydrogens to our carbon, so we've really reduced it down. And nothing will happen at this point, just like in Grignard reactions. This molecule will sit here. There'll probably be a lithium counter ion there, but nothing is going to happen until you do the final step where you add water to quench the reaction. And when you add the water, you do it slowly, maybe on ice, because it is a very exothermic reaction. But we're going to protonate that oxygen, and that's how we end up with our alcohol at the end of this reduction. Okay, so those are the 2 mechanisms. The thing to remember is they're not really new. They're just like the Grignard mechanism that we already learned. So now this would be a good point to stop and try number 3 on our worksheet. So if you want to pause the video and try number 3, go ahead and do that now. And when you come back and start up the video, I'm going to go through the solution. Okay, so number 3 on the worksheet basically asks us to predict the products in the different reduction reactions that are shown. So 3A, we start with a compound like this. So the key thing to do in these reduction reactions is to know which reagents do what and to be able to identify your functional groups. For example, in my first reaction, I have sodium borohydride. Methanol is just the solvent to protonate at the end. But sodium borohydride, if I remember that this is a mild source of H-, then that means that it's only going to be able to reduce ketones and aldehydes. But up here we have an ester. Esters do not get reduced by sodium borohydride. So nothing will happen to that part of my molecule, but my ketone will turn into an alcohol. So we leave the ester unchanged. Ketone becomes an alcohol. Okay, I'm going to skip over to letter C because I think that one's another fast one to answer. We have a carboxylic acid on one side of this molecule and an aldehyde on the other. And now we're using lithium aluminum hydride, and working up with water. And by the way, your book sometimes abbreviates lithium aluminum hydride as LAH. That's the same as lithium aluminum hydride. So you can do it either way. Okay, so lithium aluminum hydride is our strong source of H-. And so that's going to reduce all of our carbonyl compounds down to alcohols. It's going to reduce my aldehyde carbon, and it's going to reduce my carboxylic acid carbon. So I just have to make sure I draw 1, 2, 3, 4, 5 carbons. This is going to become an alcohol. 1, 2, 3, 4, 5. And this is going to become an alcohol over here. So that would be my product after using lithium aluminum hydride. Okay, letter B. Go back to this one. This one I saved till last because I think it helps to kind of think through the mechanism a little bit to figure out what the answer is. Because in letter B, what we have is an ester, but that leaving group, the thing that would normally get kicked out and leave, it's tethered to the rest of our molecule. And so we have to think about what it's going to turn into at the end of the mechanism. So if I'm adding lithium aluminum hydride, remember that's just a source of H-. That's initially going to attack, kick up, and then eventually those electrons kick back down and kick out the leaving group. So I'm drawing a lot of arrows in one picture. This is not how I would draw a mechanism, but for the sake of just thinking through the problem, what I'm initially going to get is something like this, where this oxygen has been kicked out as a leaving group. But I can't just stop drawing it because it's tethered to the rest of the molecule. Okay, so that's after 2 steps of my mechanism. And then another hydride ion comes in, attacks a second time, kicks up. We've still got this O- over here. Now we've got another O- here. And we've at this point added 2 hydride ions to that carbonyl carbon. And now again, this molecule just sits here. It's got some counter ions here and here, but it's not going to react any further until the water is added. And as soon as the water is added, I guess we'll need 2 molecules here. This guy's going to get protonated, this alcohol is going to get protonated, and at the end of the reaction, we've got a molecule that has 2 OHs on it. Okay, so that's it for reduction reactions. We'll pick up in the next video with oxidation reactions.